gotten helium-filled balloons before, you may have noticed that when you first get the balloons, they float up in the air. But when you come back the next morning and look at them, all of a sudden they're not floating in the air anymore and they look a little bit deflated. We're going to use the balloon as a model for a cell membrane and explore why some molecules can get through the surface of the balloon while others cannot. So we're going to use an ordinary balloon, and I have some vanilla extract. I'm going to put the extract inside the balloon, inflate the balloon, and then tie a knot in it. So if you look at the balloon, you can kind of see where the vanilla extract is. But when I shake it up and I smell it, sorry you don't have smell-o-vision, but it smells like vanilla. How did that happen? How did the molecules for the vanilla extract get from inside the balloon to outside of the balloon? Well, if we looked at a latex balloon through a very powerful microscope, we would see that what looks to our eyes like a solid sheet of latex actually has small pores between the latex molecules. And then when we inflate the balloon, we stretch those pores even larger. And so if the pores are larger than the molecules of the vanilla extract, then the vanilla extract molecules can go from the inside of the balloon, pass through the surface of the balloon so that we can smell it on the outside. So, what if we take that same balloon and fill it with water? If I take this water balloon and I weigh the mass of it at the beginning and then let it sit overnight, when I come back the next morning and weigh it again, the mass isn't going to change. It's going to be the same. So what does that tell you about the difference between the size of the water molecules and the size of the pores in the balloon? We can use the balloon as a model for a cell membrane. So as you go through the Smelly Balloons worksheet, just kind of remember what you observed in this demonstration and use that to help you answer the questions.